Hi, everyone. My name is Hong Bong, and I am a program specialist working at NASA Ames Research Center's Technology Transfer Office. And I would like to welcome you again to the NASA's Technologies of Tomorrow's webinar. NASA Ames is one of 10 NASA centers located in the United States, and we are known for our intelligence and adaptive systems, or entry systems that make sure spacecrafts are safely delivered to Earth and celestial bodies, our advanced computing and IT systems, our aerospace divisions, wind tunnels, astrobiology and life science, our air traffic management systems, and our space and science divisions. The primary purpose of a lot of people like to know, what is NASA Technology Transfer Program is. Since its inception over 50 years ago, NASA's Technology Transfer Program ensures that innovations developed for exploration and discovery are broadly available to the public, maximizing the benefit of the nation. Whether you're looking to start a new company, enhance an existing product, or create a new product line, you can gain a competitive edge in the marketplace by putting NASA technologies work for you. Um, and why should you license NASA technology? NASA license allows access to a technology for testing and implementation into a system, service, or product that could result in sales. The NASA Technology Transfer Office cares about success of the commercial businesses, and negotiation of terms is done but on a case-by-case basis. And a lot of the different companies that do end up licensing NASA technologies have multiple successful commercialization licenses with us. So these licenses are published on our NASA spinoff website. Some of these spinoffs include the anti-icing formula that helps prevent train delays. This technology was developed at NASA Ames when we needed a non-toxic, biodegradable, and cost-effective substitute for uh, ethylene glycol. A company used NASA's formula that was originally created for use on military aircrafts and used this to enhance their existing anti-icing technology to create a brand new product that was used to prevent ice from sticking to train tracks and its switches. Another great example of a NASA spinoff is the memory foam, which was developed in 1966 to improve the safety of aircraft cushions. This led to the company taking that innovation and creating it for what we know as today as the Tempur-Pedic mattress, which is now widely used at many homes in the world. There are multiple examples up to 1,700, and they're all available on the NASA Spinoffs Technologies website, which you can, and our annual spinoff publication, which is searchable online. And a lot of these spinoffs actually started with through licensing. So a lot of people like to know, how do I get a license and where do I start looking for technologies that might benefit our company? These innovations can be discovered on our NASA Technology Transfer Program website, which is located at technology.nasa.gov. This website is easy to navigate, and you can use the search function to using key descriptive words, or you can simply click on the patent portfolio link at the top of the page. This link leads to the different categories. We have up to 15 licensable technology categories that you can choose from. For example, let's go ahead and click on instrumentation category to see what many different technologies you can choose from. And on here, you can see that after clicking on that, the link brings you to a page of different technology you can search through. There's also the search bar there. And I'm going to run you through a kind of example how someone looking for a license can kind of navigate to the website. So From here, let's click on the real-time radiation monitoring using nanotechnology, and it'll lead to our patent portfolio top sheet. So on here, you actually has a fact sheet that shows all the information on the technology, a list of its benefits and possible applications. And you can also, if you have any questions regarding the technology, there's links at the top and bottom of the page. From here, you can also click on to download the fact sheet as a PDF. So it's easy, you can easily share it with through email, or you could actually print them out and as handouts for your team. And it makes it easy to share. And there's also links to the USPTO website patent filing, which is at the bottom of the page here. So when you click on that, it actually leads to our patent claims and description. And on here, you actually read through the full information on the patent and its claims to make sure your technology meets your needs. And if that technology does meet your company's needs, you can apply for a license. To apply for a license, you can either go to our technology.nasa.gov/licensing page, or you can click to the top right of the information fact sheet to apply for a license. And from here, it will lead to our licensing page, where you can create a guest account to apply for your license. You will create an account. I would suggest you use a company email address instead of a personal one. Once that account is created, it'll bring you to the licensing application page. On there, you'll be asked a series of, you choose what type of license you want. I'll ask you a series of questions on what your company does and how you plan on using this technology. You want to put as much information as you can as possible. The more information, the better, to help us better review your request. So, types of licenses. We have an evaluation license, which is an option for a company to explore the potential of a technology and learn from it to see if it fits your business goals. All these evaluation licenses are non-exclusive agreements without any long-term commitment. They do come with a one-time fee. These licenses range anywhere between 6 to 18 months, with most of the licenses lasting about a year. Evaluation licenses are not permitted to commercialize or sell the technology. A traditional commercial license after the fact will be needed to do so. And then we also have our commercial license, which is a standard one, which is for companies to make and sell products using NASA technology. And the terms of these licenses are done negotiated on a case-by-case basis. Then we have our startup licenses, which come with NASA, when NASA waives the initial licensing fee. There is no minimum fee for the first 3 years of the license, and letting companies on to the cash while securing their property needs. This is a non-exclusive license, which means companies that may apply for a similar use of the technology for commercial purposes. However, NASA will consider further exclusivity if the startup wishes to negotiate those terms. On top of licenses, NASA also offers software, which is actually free to use. There are different types of software available. It's all on our software.nasa.gov. Anything that's not open source will require a software usage agreement, which usually goes from government purpose to general purpose. We're a U.S. and U.S. firm, and also there's public release. Government purpose, of course, requires you to have either a government grant or contracts for you to apply for use of the software. But we have hundreds of software on the website for you to search through, with majority of them being open source. And here's a link to our different resources and links. So we have our technology transfer, how to license if you need any more licensing questions, our patent links, our free software link, and SBIR, of course, our spinoffs, and our home and city link. If you have any questions regarding how to license or any technical questions on the portfolio itself, you may reach out to Jason. And if you have any general questions for software release or list licensing in general, you also reach out to me. Our contact links below. And I'd like to thank you again for attending our webinar today. Thank you.
Okay, so thanks for the opportunity to speak. So I'm going to be speaking about what's a diagnostic tool called Interactive Diagnostic Modeling Evaluator. Patent was issued in 2019. Next slide, please. Yeah, so sorry about the patent number there. It was the last change. So technology overview, why was it created? So IDME, it's a MATLAB application to support the creation and maintenance of D-matrix diagnostic models for NASA systems. And really, you know, as somebody who's worked in the area of model-based diagnostics for 30 years, one of the hardest barrier entry and cost drivers is actual development of the diagnostics model. So IDME acts as a regression tester for diagnostic models. And, you know, for typical NASA systems where there are thousands of failure modes, it quickly becomes unwieldy to add in one failure mode and test it and add in the next one without ensuring that the work you've done on the prior failure modes hasn't been clobbered by the new model. So in the same way that regression testing is used for software, IDME is used for diagnostic models. And so the applications for this technology, you know, our world is run by what you would call a cyber-physical system, which are combinations of hardware and software that are executing, you know, feedback control algorithms at millisecond level to achieve the goals of the system. And so there's really two components to feedback control. There's the state estimators that say, where am I, and the regulators that perform what do I do. And so these, we don't even notice it, but our whole world is running around those two loops over and over again. And what the D-matrix is it's a form of a state estimator for systems. And well, what kind of systems can this apply to? Well, it can apply to spacecraft, aircraft, buildings, cars. So like when the check engine light goes on in your car, well, there's probably a D-matrix in the logic of the car that's evaluating sensor readings to determine failure codes and medical equipment. So, you know, the technology itself is general for the deployment of diagnostic systems. And why is it better today than the prior approach? Well, for small diagnostic systems, you can do them by hand, but it's really this notion that things get out of hand when you're dealing with thousands of failure modes like the station or the shuttle or gateway that's coming up or the lunar surface systems. And you just need a systematic method that's branch and bound, is buying down the model at a certain stage, you add in the new failure modes, and it will help check you out to make sure that the model still meets the correct false positive and false negative rates required by the customer. So now I have some background slides, so next slide. So I'm going to do a little bit of a deeper dive, 5 quick slides. First is what's the D-matrix format? The second slide is where do D-matrices come from? They're really compiled from schematics. Third is really the IDME architecture. The fourth is, you know, what does input data look like to the system? And then finally, we're going to sort of summarize the 5 different repair strategies in the pseudocode of the algorithm that are part of the claims in the patent. Next slide. So a D-matrix, so if you look at, there's 2 D-matrices, an initial one. So a D-matrix is really a simple matrix where the rows are the failure modes of your system, and the columns are really where are the sensors and the tests that you want. So like if you see a 1, you know, in the first column and the third row, that 1 means that if that test evaluates to true, it's signaling that failure mode, right? And so what IDME does is, if you notice that the D-matrix on the right, everywhere there's a blue shaded square has had its value changed. So 1's got turned to 0, and then the D-matrix that you see on the right also has an additional column. They added in an additional test. So what IDME effectively does is, by playing data over time for all the different failure modes, we'll look at the current D-matrix and say, yes, you're meeting the correct false positive, false negative or no, you're not, and these changes need to be made. And the I in IDME is interactive, which is when it comes up with a set of things it flags, the user is part of that loop to determine whether to accept them or not. Next slide. So really just as a small shot of a schematic, a shuttle schematic, and it's like, where did the D matrix comes from? Well, the first arrow really, so every component in your system, well, those will become the rows of a D matrix because every component has a set of failure modes. And then every sensor reading in your system, those circles in the schematic, well, those become the beginning of the test, right? So you can look at a D matrix as that which is sort of compiling out the graph that every schematic has. Next slide. So when you're really looking at the training the data for the system, what you're doing is you're setting up a bunch of time series data that deal first with the nominal case for a component and then a set of failure modes for that. And each failure mode case is itself a set of time series data. So being a MATLAB application which is strength is the iteration and analysis of data, right? So you set up your supervised data in this form to input into the system. And next slide, please. So here's really the architecture, right? If you look at the very bottom where the person is, right? The person accepts a set of performance metrics from the customer. We're building this diagnostic system for the customer. And those performance metrics, so then the loop above the person with the DME is, so the person accepts the performance metrics. Then also above the performance metrics, you have a set of data that correspond to all the failure modes in your system and all the nominal operation. So those get input into the diagnostic modeling evaluator. And what the DME does is it suggests an arrow down to the person, which is what repairs to perform. And then the person iterates back with what repair actions do they want. And essentially at the top is the model, right? And so in this process, over time, you sort of develop a model that can meet all the supervised data that was provided by the customer and also meet the performance metrics provided by a customer. And you don't really care that this goes into the thousands. You just let it do its job in saying, oh, this failure mode actually looks a lot like that one. Should we merge? Should we split? Next slide, please. So there's really 5 strategies that get used for the D matrix. And you'll see that on the left, we list them as strategy 1, 2, 3, 4, and 5. And the first strategy, so recall now I've already shown you briefly what a D matrix is. The columns are the tests and the rows are the failure modes. So strategy 1 is, do I need to add an additional row? Strategy 1 is saying, do I have any identical rows or columns in my matrix, right? Immediately, even in that matrix right there, that's a non-trivial task, pattern matching task for a human to do, but it's easy for the machine. Strategy 2, change the rows of the D matrix. It says, I haven't modeled this failure mode. I need to insert a certain failure mode, or I need to remove a failure mode. Strategy 3, so recall I said that the tests were all the columns, right? Well, what is a test? Well, a test is an arbitrary piece of logic in the specific domain of the system that evaluates to either true, false, or unknown. And that logic is called wrapper logic. So strategy 3 says you need to change your wrapper logic. What's the classic case of that is that, say you have a parameter that has a red line limit. Well, red line limits on the ground are maybe slightly different than red line limits in space, right? Oftentimes, once a spacecraft is launched, they have to recalibrate red line limits a little bit because there isn't convection in space and other things apply. So strategy 3 helps change the logic for your test. Strategy 4 really is back to the issue of, is there a 1 or a 0? Does this test map to the failure mode or does it not? That's strategy 4, change it. And strategy 5 is really adding in different columns, right? And so what happens, if you look over on the right where I say IDME pseudocode, what you're really doing is 3 levels of loops. You're looping through all of your failure cases, your repair cases, and you're looking through each of the failure cases, and then you're looking for all the time steps. And in doing that process, the tool will suggest to you that you need to perform one or more of the repair strategies. And so essentially that was the development of the algorithm, and really address a continuing need, which is, hard coding and developing the diagnostic models is a time-consuming and very expensive process. So this tool was meant to find that line between full automation and a manual process that's being used today. Next slide. I think we're done. There we go. So you go back to the first slide. Any questions by any chance?
Thank you, Peter. That was fantastic. We will wait to see if there's any questions in the chat. Please feel free to put any in. But I'm going to ask the same question that I asked before. If a commercial company were to license this technology, what do you expect it would take them to take this license patent into a final commercial product?
Well, somewhere there is, I worked on this 12 years ago, so somewhere there is a MATLAB code base for that, right? So in the same way that, first they would have to make that decision, are we going to make this a MATLAB application or not? I feel like that's a MATLAB is still very relevant, so leaving it as a MATLAB code base would be proper. And then you would want to market it as a plugin, just like you have Control Toolbox and Stateflow, which are also plugins to MATLAB. You could imagine there could be a D-matrix authoring environment for MATLAB as well. So that would be the route that I would take.
Got it. Yeah, that makes sense. We had one question in the chat. I think this goes back to one of your slides. It says, what is the extra column added to the matrix on the right?
Oh, in this slide here?
I believe so, yeah.
Good question. So you have to remember that oftentimes the state space of a system is much larger than the number of sensors that you have. It's a many to one, right? And so essentially, adding an additional column basically says I'm adding another test to my test suite to help me differentiate, say, between one failure mode and another, right? So that's kind of what, you say, well, maybe I can run this piece of analysis over this combination of sensors, and I'll add that as a test. So additional columns imply you've added additional tests. And the key thing to understand is when you add each test, it's got to take a position for every row, for every failure mode, right? The whole notion of the D-matrix is more general than this patent. There's a company called QSI that uses D-matrices, but the notion of the D-matrix has been around for 30 years in that format of test versus failure modes. You can also learn these through, so did that help answer the question?
Yeah, I believe it did. Thank you. That was very interesting.
Sure.
Yeah, thank you, Peter. For the sake of time, we will move on to our next question or next presentation. Sorry, which is going to be variable geometry aircraft being supported by struts and/or trusses.
Okay, thanks for your time.
Thank you, Jay. This is John Melton. I'm an aerospace engineer in the systems analysis group here at NASA Ames. And we're going to be talking about a twist on an old idea. You've already seen some pictures that of the very famous AD-1 oblique wing aircraft, and we've got a slightly new take on that. So go ahead, next slide there, please. Why was this technology created? Our airports are filling up, and it's getting more and more difficult to bring in larger airplanes of the 737 and larger size. And by using what has historically been called a skew wing or an oblique wing, you might hear that in the literature as well, you can improve the aerodynamic efficiency of the vehicle over its entire flight envelope. So that means not only in cruise, but also during takeoff and landing. Because you can unsweep the wing, you can eliminate some of the complexity of the mechanics that have to be in the wing in order to drive complex multi-segment flaps. And you can also improve your climb rate when you're leaving the airport. And that's important because that means you can actually reduce the thrust and therefore the noise. When you're on the ground, instead of having very large wings or having to fold wingtips, you can really reduce the footprint of this vehicle. So you could even imagine two vehicles passing potentially on a taxiway, and also reducing the probability of a ground or a taxiway collision. Now, with the addition of the strut, it really has two uses. One is to improve just the structural efficiency of the wing and the pivot, but for aircraft that want to carry their engines out on the wings, and there's a variety of reasons why you'd like to do that, the strut actually can be used to kind of create what's called a 4-bar linkage, and it helps keep the nacelles aligned in the direction of motion regardless of the wing sweep. Finally, I've been a strong advocate for what I kind of call transitional vehicles. We see a lot of vehicles, and specifically aircraft, in the literature that talk about very complicated cryogenic vehicles with hydrogen, and they're typically these very large wing bodies and a lot of complexity and difficulty in manufacturing of those, whereas the skew wing, and especially the skew wing with the strut, really allows us to continue to use the kind of tube and wing infrastructure that currently exists for manufacturing. And that tube and wing infrastructure has a lot of advantages. It makes it very easy to lengthen a fuselage or shorten it in order to scale vehicles for their intended market. And it also really simplifies the manufacturing and the jigs and all the other things that go into the construction of an airplane. And we have such a great amount of experience with tube and wing vehicles. So the pictures there in the upper right. And again, I'll just talk a little bit more about some of the benefits. By modulating that sweep, you can fly at the best aerodynamic parameter of the vehicle for the entire flight. And that's usually expressed as the Mach number times the lift to drag ratio. I was recently on a flight back to Chicago where I think we spent the entire time from the Mississippi River on the west side of the state to Chicago slowed down by air traffic management. So here's this airplane that's designed to cruise at 7.5, 0.8 Mach number, slowed down to 250 knots, and not operating at its most efficient ML/D number. So as arrival spacing delays grow and things like that, you can slow this airplane down but still be fuel efficient. We can go to the next slide. So I was just going to end this with a statement of the patent information there and 4 figures that were taken from that patent that show the improvement of that ML/D parameter, Mach number times lift to drag ratio, for the variable geometry aircraft versus a recent 737 model, both in cruise and at takeoff and landing. And while you might look at, let's say, this cruise ML/D number for the 737, and here in this picture, it shows a value of about 13.5 at the cruise Mach number. That number jumps up to over 14 for the oblique wing geometry vehicle. And very small changes in that number are actually economically extremely significant, both to the airlines and to anyone looking at aircraft performance. And similarly, we see that for the takeoff and landing. And again, think of takeoff and landing problems as being almost in the future more noise and space dominated than necessarily specifically aircraft performance, but that unskewed wing lets you take off much more steeply, land at a slower speed, requiring a lot less thrust and a lot less community noise. So that's what I have for this presentation. And I think, Jay, I'm going to follow this one up with a second presentation, but I'm happy to take some questions about this one now if that's the way you'd like to do it.
You can do your second presentation, and we can just answer all the questions together.
Okay, great.
Great.
So we'll move on to the second presentation. It's for a system called Maestro, Airborne Machine Learning Estimates for Local Winds and Kinematics. Let's go to the next slide. So Maestro was developed to overcome some of the extreme challenges of flying both unmanned vehicles as well as air taxis within cities and within urban and complex topographies. Now, urban flight operations are obviously very complex, and all of us know how the winds are really influenced by the buildings. And this is specifically or especially so during takeoff and landing of the vehicles. Now, our cities are also dynamic. You think you might have a model of the city, but a couple months later you find out, hey, there's a new building here, or my map was incorrect in the first spot. So you can't always completely trust the computer model that you might have of the cityscape. And there's also additional challenges with the reliability and the accuracy of a GPS type signal that faces a lot of spoofing, shadowing, reflection challenges when you're operating within the city itself. So we wanted to come up with a low size, weight, and power solution that doesn't require a lot of airborne computation, doesn't require flying a supercomputer on board each vehicle that might be flying within a city. And we do that by capitalizing on machine learning. And if we go to the top right picture, this is kind of the elevator pitch of how this works. Each vehicle would be equipped with basically one of these type of LiDAR systems that you currently see on a lot of autonomous driving vehicles, autonomous cars. That system has a laser beam setup typically that sends out laser beams all around the vehicle. And by recording the time that it takes for that laser beam to reflect back, you can create what's called a local depth scan. So instead of a normal picture, what you get back of the surroundings is you get back a picture that basically has information in it about how far it is to a hard surface. So buildings that are closer to you show up in red, buildings that are farther away would show up in blue, et cetera. But it gives you that idea of where you're at relative to all the buildings around you. Now, what we've done is trained a neural network to understand that relationship between how far I am away from all the surrounding buildings in order to create an estimate of what the surrounding wind field is. So as I'm traversing this city, I'm automatically, without direct measurement, generating an idea of where I think urban urban gusts might be, where wakes of buildings might be, and that so that I can now pick a path for my UAV to improve or to reduce the possibility of potentially colliding with a building, perhaps reduce the energy that it requires for me to traverse to the next waypoint, and really significantly reduce the accelerations that a passenger or a sensitive cargo might be subject to as we're flying through the building. Now, the other thing that is in this patent is one of the earliest references to using this type of machine learning estimation in order to actually act also as just a substitute for your position and your kinematic information. Let's go to the next slide. Here, the big picture kind of shows the elements that you're seeing of the movie that's in the top right. The movie in the top right is basically showing how this system works by scanning each time as this vehicle moves through the city, scanning the local environment, making a prediction of the wake, and then comparing it with what we know the known flow field looks like. This runs incredibly fast, and I suspect that this will be a system that's on board most air taxis and UAVs operating in complex terrain, whether that be a city or a shipscape or a port, etc. And really doesn't, it also doesn't necessarily require a LiDAR. When we developed this patent at the time, there wasn't the availability of kind of stereo cameras that now have this ability to also create that depth image of your surroundings. So you're not restricted only to LiDAR now. There's even lower cost systems for 360-degree stereoscopic cameras that could also be used in this system. Let's go to the next slide. And this is my last slide. If you'd like to find out more information about this, we have 2 papers at the upcoming IEEE International Conference on Robotics and Automation. That's going to be in Atlanta, Georgia, here in another 2 weeks. Some of this work is being done with the GRASP lab at the University of Pennsylvania, one of the country's premier robotics labs. And in these 2 papers, we show some early experimental validation now of this concept, and we go into some of the mathematical details of how the process works. Finally, there on the bottom is a listing of the patent that's associated with this and my co-inventor, Ben Nikaido's name. I think that's it, Jay. I think I got us to do it by 12 o'clock Pacific here.
Yeah, that's fantastic. It was, both these technologies are great, and thank you for going over them. We had one question for your first technology. The skewed wing will require a T-tail. Is that correct? If so, that will be disadvantaged from both structural and low-speed aero perspectives.
No, that's actually not correct. And I would like to recommend for people who are interested in skew wing aerodynamics, there's a fantastic NASA special publication that was put out, I want to say about a decade ago, called Thinking Obliquely. And it talks about the long history of the skew wing up through the development of the 81. And I think he has showed a picture of the top-down view of the 81. That aircraft was flown down at Dryden / Armstrong Research Center at Edwards Air Force Base. And that vehicle was not a T-tail. So no, there's no requirement for a T-tail for a skew wing vehicle.
And for that first technology, are there, for commercial airliners, are there any sort of commercial airline that has truss-based wings that can use this technology, or would that have to first be adopted and then they can use this technology? Because it
Well, if
seems
you
like it's doable for the small Cessna types that have truss-based wings.
truss-braced wing was unfortunately just somewhat shelved um, about a week ago. We did have, but Boeing has a large investment in a transonic truss-braced wing vehicle. NASA was prepared to work with Boeing to generate actually a full-scale flight demonstration aircraft of a truss-braced wing, so it can work at transonic speeds. That vehicle spent a lot of time in NASA's transonic wind tunnels. Now, it was a symmetric vehicle. It wasn't a skew-wing vehicle. But again, the skew-wing vehicle has been flown. Demonstrators of that have been flown. It just has never really caught on, partly because it does kind of look so strange, I will admit, but aerodynamically, and especially now with the advanced control systems and the advanced materials that we currently have, there's no reason, honestly, that we aren't seeing more skew-wing vehicles. And again, they really solve not only this being aerodynamically the most efficient at all speeds, but they really solve some of these terrible problems that we have at airports with just limited real estate, and larger aircraft.
Got it. Thank you. We have another question in the chat. Where will the mechanism for actuation of the wing be housed? Will there be a pod above the fuselage for this?
Typically, that that pivot joint has been something that goes through the fuselage vertically and takes a small amount of room there. You'd have galleyways usually on both sides of that pivot joint. That was the original thought because you wanted to just have as long of a moment arm to hold that pivot as possible. So putting it in just a pod itself of limited thickness is probably a little bit more challenging. However, if you were to apply this approach to a much smaller vehicle, UAV size, I think structurally there it probably works. On full-sized transport aircraft carrying people, typically that pivot goes from the top to the bottom of the fuselage.
Got it. And are there any aeroelastic advantages like a forward-swept wing?
Yeah, again, that's in both the patent and in the Thinking Obliquely. NASA SP goes through all the details of why the skew wing is so advantageous. The skew wing also is probably the best configuration for a low supersonic vehicle. So, Mach 1.2, 1.3 or so, because once you slow down, which you inevitably do during takeoff and landing, you get the advantage of having that long wing that's swept only as much as you need it. And so, again, you're maximizing the performance of the vehicle over the entire flight envelope.
Oh, thank you. For your Maestro technology, if I'm going to ask the same question that I asked the others, if a commercial company were to license this technology, what would you expect to take this to create a final product around it? Since it seems like you were saying that there are now lower cost options compared
There
to
are lower cost options for some of the sensors that that would be used. So instead of using a LiDAR, and even LiDARs now, I mean, pretty soon all of these sensors are going to be falling out of your cereal box. I mean, they really, you know, they're getting cheaper and smaller all the time. So you could do it with stereoscopic cameras, you could do it with a small LiDAR, etc. Um, and this would be put into part of the decision making that your UAV uses when you tell it to go basically to the next location. It would scan the surroundings while it's traversing between the waypoints of that trajectory and making smart decisions, seeing areas where, oh, I might expect there's a large change in the wind speed as I move behind this building. So maybe I want to shade and give a little space around there, not get too close to that building because there's going to be a strong gust that's going to come through this urban canyon. And if I move away from it, I can be a little bit more prepared. And again, maybe I can use a little less energy sometimes if I'm avoiding what might be a strong headwind if I go to the left, whereas if I go to the right, I can avoid that strong headwind, save some energy, or reduce the turbulence that my passengers or my payload might see as well. So it's I've always thought of this as kind of part of the path planning side of figuring out how do you take that next step? Because Maestro tells you not just what the wind right at the vehicle is, but it gives you that idea of what the winds are in, you know, 100 or 360 degrees around the vehicle. So you can really make that smart choice about which direction to move to next. And since it's constantly running and constantly rescanning that environment, the fast neural network uh, automatically is updating that estimate of what the winds are in real time.
And is there like this may sound like a naive question, but is there a size limit to how big the UAV or whatever is for this, or just whatever that is allowed in a urban environment?
So yeah, so I would say the answer to that is no. Now, obviously, uh, if you have a sensor package that's going to be, you know, bigger than your drone itself, that's obviously, you know, unlikely to work. But this does not require, you know, a garbage can 200-pound sensor to be lugged around with you. These lidars, modern lidars, you know, the size of a coffee cup, you know, weigh a pound or two, really don't take much power. And for the computation side, it's like you know, a laptop in terms of the amount of computation, especially now. So it's really a relatively, I mean, even a Raspberry Pi would probably be sufficient computational power to have on board.
Great. Yeah. Thank you. Thank you for going over both these technologies. I am not seeing any questions in the chat. So yeah, thank you so much. This was very intriguing and helpful.
My pleasure. Thank you, Jay. Thank your whole team for this opportunity. We love to obviously talk about our inventions, and we love even more to see people picking them up and hopefully getting them out there and helping solve tough problems.
Yeah, absolutely. And next up, we have context-based configuration management system.
Hey Jay, are we on time or are we past the schedule?
Yeah. We're a little early, so you can start now if you'd like.
All right, I'll go ahead and start presenting. All right. Hey everyone. So my name is Mohana Guram. My background is in computer science. I specialize in designing data systems for complex systems, and have been supporting multiple missions, NASA missions, doing so. So today we're going to talk about this context-based configuration management system that we designed a long time ago, almost a decade ago, actually. And it's also referred as Internet of Management Things, and you know why I'm trying to refer it using those terms. Moving on to next slide. So the problem statement, right? So whenever we design solutions for situational awareness engineering problems, the emphasis is on tools and technologies that quantify and monitor data associated with hardware, software characteristics, technical operations, and states like that, right? There is very less emphasis on human and organizational elements, but if you notice, that is where a lot of decision making happens. So here, for example, if you look at the right side picture over there, the Boeing 747, right? There's 2:1 ratio. So there are 2 humans and 1 complex system, the pilot and co-pilot, and basically the craft itself, right? So most of our solutions would be geared towards analyzing the aircraft itself, maybe from like a digital twin perspective, reading sensors data from every point of view and trying to assess the performance of the aircraft. But when we are making decisions over time with respect to the execution of that, building an aircraft or running it through experiments and all that, there is way beyond the aircraft that the information is being generated, especially from human and organizational point of view, that does not come into play. So that is one of the main reasons why we started looking into how do we address that aspect beyond just the hardware networks and software characteristics, sensors kind of thing. So that was the problem that we were trying to address, and we came up with, okay, why not think in terms of simulating the aspect of Internet of Management things from Internet of Management things point of view, and that is where we came up with some prototype to really build a system like that. So moving on, I have to give credit to Yuri Gordiak. This is basically his brainchild. So he's the one who came up with around like these 250 communication objects and associated ontologies that we can rely on to capture like critical elements related to human organization communications within the context of designing and execution of complex engineering systems. So for every visual representation over there on the right side, there is an ontology associated with it that acts like an object that can be connected to other objects to really capture the knowledge that is being generated out of these human gatherings, maybe meetings or some decision points and stuff like that. And we were basically, the objective was how can these communication objects be automatically connected together to form that knowledge graph, and so that we can assess the information that is being generated from the point of view of maybe risk or even doing background analysis kind of thing. So here on the left side of the image, you can notice that the type of communication objects that were being generated from like one single meeting, how many decisions were made, how many financial obligations were committed and stuff like that, right? So there were so many critical elements that came out of simple meetings that they are not foreseen or they're lost in email thread somewhere, but they do influence the product at the end of the day. And how do we capture that information in a well-organized way is what the objective was for the Internet of Management things. So we basically came up with this prototype and we started putting together a system where the objective was, okay, let's find out, identify these management primitives as to like what exactly happens in these high-level management meetings so that we can start associating them with these communication objects and try to capture the essence of that that piece of information from an ontology point of view and connect them to finally form like a knowledge graph kind of system, right? Then Yuri came up with this iconic representation from a visual point of view for those management primitives. Then we started thinking about how do we link these management primitives to the real world entities, like for example, the real tangible things like an aircraft or a sensor within the aircraft and stuff like that. So, and then we even thought about automating this generation of reports from all the data being captured. It was a semi-automated process. I'm going to talk more about it and the reason why this is more important in the current day in my last slide, basically. Then we started putting a platform together where actually organizations can really take advantage of this tool that gives a visual perspective of the situation in terms of awareness for the project or product that they are trying to work on. Then the application, as I indicated, we started building this metadata management system for those ontologies, and we did design many of these objects to be operational for management to really take advantage of. And here's a very simple example, right? For the Aeronautic Research Mission Directorate weekly meetings, we were capturing that information and trying to synthesize it to these ontologies, and we were generating these weekly activity reports out of this system. Just to give an insight, like for example, the 2016 weekly meeting activities led to around 700 communication objects that were further classified into like artifacts, quality context, and processing objects. So the information was very well organized, and you could get a visual sense into how the information is being spread out to multiple other centers. For example, this was run out of headquarters, and we were even tracking information that was leading some of this information to be influenced at multiple other centers like Ames, Langley, Glenn, and Armstrong kind of thing. So that's the application point of view that we really experimented with. Then the benefits, right? As I was indicating before, right, when we look at the solutions for this situational awareness engineering problems, we are focused mostly from a hardware point of view and software point of view. And that is where most of our design and development aspects are consume our time, basically. But there is a bigger entity, which is the human and organizations, and that aspect is less important from a solution point of view, and that information is just fragmented and floating around in multiple different channels. So the objective of how to capture that information, bring it into a system so that it is connected to the things that are going in the tangible things like the hardware and software kind of thing. So the other benefits obviously are improves the enterprise level forecasting and stuff like that. I don't want to read that stuff, but you get an idea as to like the kind of situation that these tools and technologies can be used for. And when it comes to the roadmap, right? So thing with the prototype that we were able to achieve was basically the agency management operation support. We were collecting information out of these higher level meetings and trying to generate reports, as well as that reports included basically the communication objects that were generated, how they are connected to each other, and how they can influence the previous reports that were generated like maybe a month before kind of thing. So all that knowledge graph was established. And we even started looking at these autonomous knowledge agents kind of thing. It was pseudo-automated, but we were trying to put processes in place so that it can capture that meeting notes and all that information and try to generate these visual representation in an automated way. It was pseudo-automated, but the reason why this is very important in today's day and age is today we talk about these AI agents and agentic infrastructures and stuff like that, which are very good at understanding natural language, right? So I wish this was available. The LLMs were available for us like a decade ago. Then this would have been like a very amazing product to sell. The reason is as soon as we plug in that information to LLM with proper guidance to come out with these communication objects and connections between them, that would have given us like a pretty good perspective on how things are being operating for a project or a product or thing. But yeah, we were just a decade old and the technologies were not there yet. But nonetheless, it was a successful prototype that was really used by projects for a while. After that, due to funding reasons, we had to discontinue it. But I think in the current day, this could have been a very good product to really play with, basically. So that was my last slide, but if there are any questions, I'm happy to answer.
Yeah, thank you so much. That was very interesting and insightful. If anyone has any questions, please feel free to put them in the chat. It's kind of similar to what I've been asking the other presenters. How long would what would a company need to create a final commercial product with this? Is this pretty plug and play, or what would they need to do? Would they need to have like the data sets and everything like that?
Yeah, I mean, for a company, it depends on their use case, basically, but the primary objective of using this product would be to build knowledge graphs from a visual point of view. And from like integration point of view, most of the technologies that were used for the prototype were open source technologies, so the technology integration would not be that challenging. Yeah, again, it depends on the use case.
Yeah, that makes sense. Yeah, I'm not seeing any other questions in the chat. So yeah, Moana, thank you so much. This was very, very interesting, very insightful. And to the rest of the people on the webinar, thank you so much for tuning in. We will be sending out an email with the video recording, and the recordings will be on the technical overview preview pages for each technology. Thank you so much, everyone. Take care.